So
Okay,
that's
Morel, are we going?
Yes.
Okay. All right, so let's talk about cluster number 5, because that's kind of one of the more difficult ones, okay? So here's the story. So this is unique because of the fact that you have series and you have parallel, okay? So to figure out that current, the first thing you do is that you look at this whole thing and you figure out the equivalent resistance, okay? It's the first thing you have to do. You are screwed otherwise, okay? So you look at this and you've got, these two are in parallel, so you're going to have 1 over 10 plus 1 over 40, and the inverse of that, and then you have this one that's in series, plus 10. Okay, so the first thing you've got to figure out is the equivalent resistance of all of that, which is going to be, what's that total?
18, maybe.
That
Is it
sounds
18?
right.
It does? Okay, cool.
No,
Oh, okay.
it doesn't.
8 plus,
Yeah, it's 18.
It is 18?
yeah.
Okay. Oh, that's 18 ohms. Okay, I was looking at something else. Okay, so there's the equivalent resistance of this whole thing going through there. So then you convert it up. Now you know that resistance, you know the voltage, and then you can calculate the current that's going through this. Now, the kicker is that current is going to get split when it gets to here. And so here's the deal. Just think this through. Which one's going to have more current going through it? The 10 ohm resistor bulb or the 40 ohm resistor bulb?
10.
10. It's easier. Mother Nature goes, hey, this is easier. So you know what that current is going through that low resistance bulb has to be bigger than the current going through that high one. Now, when you're looking at power, and power determines brightness. So I can't emphasize this enough. You have to be fluent in the 3 languages of power. You've got to use your basic one, which is PIV. That's cool. You can also use I squared R. You can also use V squared over R. Okay, those are the 3. And like I said, you have to pick your battles in terms of how you're going to calculate that power. And if you're on the test or whatever, and you flip out, you go, man, I don't know how to come up with those. Well, just start with the idea that you have verb. Oh, if you solve for resistance, that's V over R. Okay. So then, if you look at V over I, V over I. And so then, if you look at PIV, then you can put that in there you can substitute that in. You got to be able to come up with these. So here's what you should see. On the current in that LB on number 5, because if that's wrong, about everything else is going to be wrong. That should be around 0.9. And the current going into H on 5 should be around 0.2. Okay? So those should be those values. Something around 0.9, something around 0.2. But what you should see is, in spite of that, the different currents, you should see that they end up with the same voltages. Okay? So those voltages on cluster 5 on the 2 parallel values both should be around 9. Okay? And then your power, oddly enough, should be much, much lower in your H1 than the low one. Because so here's what people the assumption that people make is like, oh, that has a high resistance, that should produce a brighter bulb. Okay? It's not. If you look at this in terms of power, and especially when you look at I squared R, because of the fact that I is squared, subtle changes to that current, because it's squared, is going to make more difference than changes in that resistance. Okay? So that's going to be the key thing on that one. So when you answer that question on the bottom of that front page, even though the 2 bulbs have the same resistance, why is there a difference in the brightness? I don't care how you answer that. okay? But when I'm asking you about brightness, understand that I'm talking about power. And you can pivot up, you can use I squared over R, you can use V squared. I don't care, okay? Just pick one and then stick with it, okay? And then you just can't say, oh, it has more current, or it has more resistance, or it has more voltage. You have to explain it in terms of one of those questions. Okay, now let's talk about that last question on that last page. Okay, so I'm going to show you a couple of ways you can do this. By the way, the test is going to be Wednesday. So we got capacitors to do on Monday, review on Tuesday, test on Wednesday. So that's how that's going to play out.
Did you move it forward?
Well, no, I thought about having it on Tuesday. I actually moved it back to Wednesday.
Oh, that, yeah, okay.
Yeah.
Eight. What did you say? 0, 1. Oh, I thought they go opposite. Oh, because it goes opposite.
Also, I use each of the
Oh, I got that one right. And this one.
Okay. So
I see.
I'm going to kind of go through both ways on how you can get this thing started. Smash mouth and the more elegant approach.
Is this
You
the
end up
AP
with
one?
Huh?
Yeah.
Is this the AP question?
Yes.
Okay, cool.
Yeah, this is the AP question. So if you do the smash mouth, there's no current going through there. You have two bulbs that are in series. So if bulbs are in series, how do you calculate the resistance?
Sum them up.
Add them straight up. No inverses, nothing. So if that's the case, then the equivalent resistance, if you just do smash mouth, is going to be 10 ohms plus 10 ohms, which is going to get you 20 ohms. Okay, there you go. Now, if you assume that there's a 20-volt battery, that way everybody's kind of working off the same one. And then if you vert it up, and you take that 20 volts divided by the 20 ohms, you're going to get 1 amp. Okay? Now, if you look at your power, and fundamentally, when you're asked brightness of bulbs, I can't emphasize this enough, brightness is equivalent to power. Okay? And that's what you have to calculate, because watts is joules per second. How much energy per second is that bulb going through? So then, if you look at I squared R, oh, okay, well, I got 1 amp squared plus that resistance of, or times that resistance of 10 ohms, then you get 10 watts. Okay? So that's what's going to happen. So each bulb is going to have the same brightness because they're in series. Nothing's going to change. Boom, here we go. Okay. Now, if you want to go with the elegant approach, okay? So that's just going to be R plus R, which is just 2R. Okay, it's a pirate thing, R plus R, right? I got 2R. Okay, there you go. So then, to get your current, oh, okay, that's just going to be voltage divided by 2R. Okay, so if you're going to go with the elegant approach and just work with this, if you want to leave it in terms of the fancy E, which is EMF, electromotive force, which means the same thing as voltage, that's cool, okay? Whatever works for you. So then you get done with that, and then you go, okay, I'm going to substitute that into power, and I'm going to get I squared R, so I'm going to have V squared over V over 2R times my resistance. So this is where it gets a little bit cool. So then you get V squared over 4R squared times R, which works out to 1/4 V squared over R. Okay? So that's the other one. You're going to get the same answer. Because now, the beauty of this is, and here's the advantage of the more elegant approach, this works for any situation. So if you plug in that voltage, if you plug in the numbers, like what we said, you plug in the actual values of voltage and resistance and take 1/4 of that, in this situation, you would still end up back at 10 watts. Okay, so no matter how you do this, you have to establish a baseline and go, this is the power without the switch closed. Okay, so that's the main idea. Now I want to close the switch. So when you close that switch, what's going to happen, and here's the bigger idea. When I close that switch, what's going to happen to the total resistance in the system?
Decrease.
It's going to go
Down.
down. Why?
Because. Go ahead, Louis.
Go for it.
Nope, it's okay. You got it.
You sure?
Sam?
It's in parallel,
So what?
so it's the 1 over plus 1 over, and then the negative first.
Because you're adding the inverses?
Yes.
Yes.
Okay, now, that's somewhat counterintuitive. You would think, wow, we went from 2 bulbs to 3 bulbs. Okay? The resistance should increase because now we're lighting up more bulbs. Okay, that seems logical, right? More bulbs, more resistance, but they're in parallel. Okay, and that's going to be the key. Bless you, Louis.
Excuse me. Thank you.
Because
Doesn't
they're
really
in
make
parallel.
sense.
Now, if you're going to do the smash mouth, okay, let's do smash mouth.
Is this part B?
No, this is, well, basically, we're going to do a comparison, okay?
I'm confused on part B.
Hold on, we'll get there. Just chill out. So, then you're going to sit here and go, okay, now that I have closed the switch, okay, and make sure that I see this on your paper. Do not just make this one big problem and think, I'm going to know when one section starts and the other one begins. You clearly label these different sections, okay? I want to know, I'm not going to go through this and try and guess what you have done, okay? So I'm going to close the switch. So I still have that 10 ohm resistor out there by itself, but now I'm going to take 1 over 10 plus 1 over 10 and the inverse of that, and you do all of that and you get 15 ohms. So here's what I want you to see. It's exactly what Sam and Morella talked about. When I had 2 bulbs in series, that was 20 ohms. When I take 2 bulbs in parallel and add that to a bulb in series, I drop my resistance down to 15. So how this plays out if you're an electrical engineer, okay? Let's say that this is the task, okay? This is how it plays out. You're saying, okay, if these were actual resistors, you say, hey, I have nothing but 10 ohm resistors. So the question is, how can I take nothing but 10 ohm resistors and build an equivalent resistance of 15 ohms? Oh, okay. I take 2 of them, I put them in parallel, I add that to 1 in series. Even though I have nothing but 10 ohm resistors, I can build a 15 ohm equivalent resistance by putting 2 of them in parallel and 1 of them in series. Okay? So that's the game that you play with resistors in terms of how you add them in parallel or in series. Now, when you do the math, okay, look what's going to happen here. So now, if you ver it up, okay, so now you take that 20 volts, and you divide that by 15 ohms, you get 1.33 amps. Now, here's the bigger picture. Why did my current go up?
Because less resistance of the whole entire circuit.
Exactly. So now there's less resistance in the entire thing. You still have the same voltage, and this is this classic situation where you have to keep in mind what you're holding constant and what you're changing. It's still the same battery, okay? It's still the same battery. So when you look at this, hey, now my current has gone up because I have the exact same voltage divided by a smaller resistance, I get a bigger current, okay? So if you're ever a homeowner, okay, and especially true of like older houses. Let's say you're renting a place in Lawrence, okay, like an actual house or something. And all of a sudden you start throwing fish. Is that your phone?
No.
You're sure?
Yeah, it's my calculator.
That certainly looks like it.
I think that's a bold-faced lie.
Maybe. I'm known to lie.
Bold fish.
Where's that phone supposed to be? What was the contract you signed? That all of you signed?
You know what?
No.
That's a good point, actually.
What if it's like right in front of your eyes and you can see that I'm not on it? I just put it like right
What
here,
if
you
I
know?
said my mom was texting me
Yeah, ask me.
about my doctor's appointment today that I had?
It's not happening. It's not happening.
Dude, just shut up.
I agree. Also, is this make sense? Is this okay?
Okay, you're asking a
You're like 10 feet
56-year-old
away.
physics teacher without his glasses to look and see if.
Well, I color coded it so you could see that. Because I kind of like put them
That's
close
not
to
how
each
that
other.
works.
And I put close switch, and then I made this section. And I said open switch, I made it yellow. And I also highlighted open as yellow and close switch as green. Yeah. Oh, that's, I just circled the like little eyes so that you can see.
Makes sense, bro.
I feel like,
All good.
is it gonna be okay?
Oh, see.
Okay, it's still like in chronological order. It's just
Okay,
like,
anyway, back to our
yeah.
story. Back to our story. Now, when you look at your power calculation, assuming that, and then here's the story. Once you begin to calculate power in one method, if you're comparing them, you stick with that method, okay? Don't do one calculation using PIV and then you move to the next section and then you're going to use I squared R, okay? You have to stick with a particular method how you're calculating power. That way it's consistent. Okay, so you do this and you take the 1.33 amps squared times that resistance of 10 ohms, and you get 17.8 watts. Okay? Now, you want to make a comparison. Okay, so the disadvantage of this method is that it's, because it's less elegant, the only thing you can do is say, okay, this is 17.8 watts. When it was open, you had 10 watts. Okay? So clearly, what's happened to the brightness of the bulb?
Increase.
It's increased. Now, so about the only thing you can do here in a comparison is to take that 17.8 watts, divide it by 10 watts, and you get 1.78 times brighter. Okay? So it's not very elegant, but it works. Hey, it's almost twice as bright. Okay? There you go. Now, the advantage of the elegant way, the algebra is a little bit trickier, but you see a more pure mathematical comparison. So if you do it with, on that elegant approach side, so now you have 1 over R plus 1 over R, and the inverse of that plus R to get your total resistance. So when you do this, okay, when you take 1 over R plus 1 over R, where's that at? I lost that somewhere.
3.
You get 3 halves R.
Oh my god.
Okay? So again, if you look at this, even if you're comparing on that elegant side, if it's just straight 2 that are in series, that resistance is 2R. If it's in 2 that are in parallel and 1 in series, then it becomes 3 halves R. So that's the advantage of the elegant approach. You go, oh, I went from 2R to 1.5 R, and now it becomes 1.5. It's easier to see that comparison. Now, if you go to the power calculation of I squared R, okay, so let me back up. You got to vert it up first, okay? So then if you do that, you get I equaling V over 3 halves R, and then that flips up, and then you get 2V over 3R. Now if you take that and put that in here, then, and that's going to get squared, so you get 4/9 V squared over R squared times R, and then you get 4/9 V squared over R. Now, here's the deal.
Wouldn't the R's cancel?
No, because that's
That's
R squared.
I gotcha.
So that's where that comes from. So look at this. Now it boils down to how well do you know your fractions. So this is more elegant approach. You get 1/4 V squared R. If you do it with this way, you get 4/9 V squared R. So which is bigger, 1/4 or 4/9? 4/9. So if you go with that approach, you're going, oh, that 4/9 V squared R, V squared over R is bigger than 1/4 V squared over R. Okay, and that's it. So again, I don't care which way you like. Now here's the beauty of this is now when you do a comparison. So now, if you do that comparison, then you're going to take 4/9 V squared over R.
Didn't you change things though?
What do you mean?
You went from I squared R to V squared over R. Didn't you just tell us not to do that?
No. I substituted that into I squared R. So I first solved for my current.
Oh, so we can use them?
Oh, yeah.
Just like, gotcha.
And then I took that current and put that into I squared R.
Okay, I gotcha.
Okay?
Yep.
So then if you take 4/9 V squared R and then compare that to 1/4 V squared over R. So this is a more, now you actually see a better idea of this comparison. So then that flips up, that 4 flips up and you get 16/9
times.
V squared over 16/9 times greater, okay? Because your V squared R is going to cancel out. So it's 16/9 times greater. Now, out of curiosity, Louis, somebody have their calculator. Monroe, you have yours. Take 16 and divide it by 9.
1.7.
Okay? And that's basically what we got when we did the Smash Mouth physics. And we did a comparison. And we got like 1 point. It's the same thing. This is a little bit cleaner because now you can say, oh, it's 16/9 times greater versus this one is just, oh, it's just a fraction or a decimal. Okay? So that's why both of them kind of have their advantages. So, and as long as I've taught this, and some kids loathe this process. They hate working with variables. It absolutely flips them out, okay? And they like to work with numbers. So when you get on the test and let's say I give you a problem like this, I don't care who you take to the dance, whether you do numbers, whatever you do. But if you're going to do numbers, you lay this out and you go, okay, this is what I'm going to choose. This is how this deal is going to play out. Okay. Does that get you where you need to be? Did I answer
Oh,
your
I
question?
got that. I told you I need help on B.
Okay. So,
Yeah,
great.
I got that.
Oh, I thought I was done. Okay. Now, so on part B, it's kind of the same idea. So a student makes the following prediction about bulb 2, okay? So now you're going to be talking about bulb 2. So now the first one, and that's what you have to pay attention to. First one is just nothing but bulb 1, okay? Second one, now you're going to be talking about that one. So again, if you go with the Smash Mouth physics, okay? So then, if you look at that first one, which was basically already done, okay? So on that, when it was just those 2 bulbs that were in with the battery, okay, you can calculate that power, okay? It's just by itself. Now, here's the deal. If you look at what's going to happen now when that gets split, so let me give you a hint. When you split it, okay, what's going to happen to the current going into each bulb once it splits?
They're equal. Aren't they equal?
So here's my question, okay? Let me rephrase this a little bit. So here's, if you leave that out of the first one, you know how much current is going into the bulb when it's just 2 bulbs in series. So here's my question. When I put that second bulb in parallel, what happens to the amount of current that that initial bulb got? Did it increase, decrease, or stay the same?
Decrease.
Decreased. So now, but what's gonna happen to the resistance of the bulb?
It's gonna go up. Up.
No. Whoa, 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 whoa.
Wait, no,
Whoa,
down.
whoa, 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 whoa,
Oh, the
whoa.
resistance of the bulb will stay
Whoa.
the
What's
same.
gonna happen to the resistance of the individual bulb?
Oh, it stays the same.
The resistance of the individual bulb isn't gonna change.
No.
Okay, that's a fixed property of the structure of that bulb.
But the
The
amperage went
current's
up.
gonna decrease.
So if you look at how you calculate power, which is I squared, if you use I squared R, okay, if you do that.
So the power will decrease.
So if the resistance stays the same, okay, if the resistance stays the same, which it's going to, what's going to determine the power?
The-
Changes in the amperage, changes in current, right? So if the current goes up, bulb's going to be brighter. If the current goes down, it's going to be less bright. Okay? So if you look at, if you were to build this, or you can do the math, whatever you want to do. So if you look at this in terms of if it's going to be less current, which is what you should see, okay, you should see that you get less current. And then if you use the argument that, because it was initially 10 watts, like I said, you already have this calculation done. So now, because this is going to get split, if you use that current times 1 minus basically 10 over 20, okay? Because this, you got, that 20 is the total of the resistance within that parallel section, okay? So basically, you're going to take the current that's going through the whole thing, okay? The current going through the whole thing, and then 1 minus that portion of it, then you can plug that into I square R. Now, on B, part 2, this doesn't ask you for like a ratio, all right? It does, you don't have to compare it like you did up on A. So all you'd have to say is that, wow, I'm using power equals I squared R. So as soon as you can prove that it has less current, and you say, hey, I've got the same resistance, that's your calculation, okay? Now, if you actually want to go through and calculate that, if you're doing smash mouth physics, and if you do that actual calculation, you should see that it drops to like about 4.5 watts. So it went from 10 watts down to about 4.5 watts. Okay?
So
Really?
does the current change then once it goes through the parallel?
What do you mean?
Like, is it?
Okay, whoa.
Okay, so like
Whoa,
you know
whoa,
how we-
shh. Which current are you talking about? Are you talking about the current in the entire thing, or the current flowing to just that bottom 10 ohm?
through the individual,
Yeah,
it's
that,
gonna go down.
yes, it's going to change, because if you look at what's gonna happen, so you figured out, so if you go up,
So should I use the one equation you showed us, the 1 minus 1/2?
I would, that's how I would.
That's what I did. So then I used the 2V over 3R because that's the overall current. And then
Okay.
I did times 1 minus 1/2.
Yeah,
And then that's going to give you V over 3R. And then the original,
yeah, V over 3R, or 1/3 VR, yes.
so 1/3.
So then when you square
And
it
then I
and
put
multiply
that into
R,
my
then you
power.
get 1/9 V squared over R.
Yeah. And the other one was V squared over 4R.
Yep,
Okay, got it. That's all I need.
okay.
Hey, Brad,
Jackson.
as a capacitor in part C, is that acting as a resistor, or is that?
No, let's talk about that capacitor.
Okay.
Okay, so when you get to that part on part C, and on a Monday, Monday's gonna be capacitor day, okay? And I'll show you this whole thing as a demo. And here's your battery, and then you got a bulb. Okay, so here's what's gonna happen. So current's gonna be flowing through, right? And initially, and on the AP, they play it one of two ways. Either right after, and the capacitor, you just insert a capacitor, and it's right after you insert that capacitor, or the capacitor's there for a long time. So when that current reaches this point, and this is right after you input that capacitor. So the electricity has a choice, and don't sit there and go, how does it know? You know, how does it know that capacitor is there? Just accept it, it does, okay? So basically electricity goes, wow, there's a path of basically no resistance if I flow through that capacitor. So initially what's going to happen is that capacitor is going to let that electricity flow through it, and there will be nothing happening with that bulb, because Mother Nature is going to go, man, I got a capacitor up there, I'm just going to let that go. It's cool, right? Mother Nature is a lazy prima donna. That's the path of least resistance. Now what happens over a period of time is that capacitor builds up charge. Now, batteries and capacitors work in a similar manner in that they both hold a charge, and then they release that battery. So if you look at your car battery, the purpose of your car battery is to hold electrical potential energy. That's what it does. So then when you turn the ignition, it takes that energy and it flows through the starter, it rolls over, your car starts, okay? So capacitors in that regard conceptually work the same way, okay? They hold charge. Now, the beauty of capacitors is that unlike a battery, you can have a rapid discharge of that energy, okay? And you get into dielectric calculations and decomposition rates. You can change how fast that capacitor releases that energy, because that's the beauty of capacitors. So what you need to know for this part, like I said, we'll talk a lot more about capacitors on Monday, is that what you need to know for now is that when you get to part B, it's going to say, oh, that's been charged for a long time. So basically what's happening is that if you think of this as being a dam on a river, after a long period of time, basically you have stored up that water behind the dam. And once that capacitor is fully charged, then it goes to the electrons, goes, you can't go through here, we're full, okay? So then, because no electrons can flow through that capacitor once it's fully charged, then the electrons don't have a choice. Then it's like, okay, well, I guess I'll go through the bulb, because even though the bulb has resistance, it's going to send that water or that current through the bulb. It won't initially, because it's easier to flow through the capacitor. But once the capacitor is fully charged, it in effect like shuts off the valve of the current flowing through the top of it and forces it all to flow through the bottom part.
So will that bulb that would be in parallel, would that be just as bright as the bulb outside?
Yes, because now it's two bulbs in series,
Right.
so they have the same brightness.
Wait, so will it like even go through that wire once the capacitor
Once that
is,
full capacitor fully charged, it won't go through there at all.
like not wow, and it just knows.
Yeah, it
That's
just knows.
interesting.
It just knows. Maybe it's an Instagram thing. It's like, oh, hey, we're looking for dorm rooms. The capacitor sends out a message on Instagram going, we're full. And then it's like, oh, okay, I guess I'll go down into the lower floors then.
Oh my gosh, that won't be us though.
They'll be
No,
living in
Yeah.
the basement.
no.
We live in the
No.
basement. Actually, don't.
Although I
like basements.
can't imagine you two living with some, two like ditzy sorority girls. So
Yeah, like nursing majors.
I can see that. I can see
No,
nursing.
nursing is like the worst. Or elementary education.
Teachers.
No, it's not that. It's just like the girls.
it's the
You
elementary.
just know. There's certain personalities and you're just like, oh dear.
Because they're going to want to mother you.
No, they're like mean girls. Like
Really?
scary. Yeah.
No.
Yeah.
Elementary ed majors?
Yes.
What?
And nursing.
See, that
That's
must
just a
have changed.
stereotype.
Because when I was at K-State,
I was just laughing at that. Oh dear.
Oh dear. Me?
Dear,
My oh
very
dear?
Canadian.
No,
Oh,
there-
no, I can't stop
there-
saying
there
oh
were-
dear. I don't
There
know.
were two majors that you could automatically spot, at least when I was at K-State. You could always spot architecture majors because they never showered and they would always just like mousse their
So
hair.
that's computer science.
No, and then they would wear gold chains. Okay, that was their moniker, right? And then the elementary ed majors you could always spot them because they always had rolls of poster board because they're always making posters, and they had boxes of like colored markers. That was the two. You could see them. Oh, elementary ed major, right there. There you go.
That's
Yep.
funny.
So I know that's horribly stereotypical, but it was true most
It's
of the time.
stereotype for a reason.
Yeah, but yeah, they were stereotypes for a reason. That's why I said if you have architecture majors that are just going to be hanging out in studio and you will never see them.
Oh, it's okay. I got Gracie.
Okay,
I probably won't see her that often though. To
as
be honest.
Gracie rolls her eyes.
Oh my
Okay,
God. Boy.
anything else? Are we good? Make sure,
So.
and again, view this from my perspective, that, and again, I don't care if they're right or wrong, but make sure on each of those clusters, you have predicted values and then you have actual values. And I'm going to be somewhat suspicious if everything you predicted was right the first time through. Okay? Generally not. Okay? But the trickier ones are when you get to, and this is where you have to look at what's happening in terms of the flow of electricity. So if you look at number 11, so let's talk about that one. So you got this battery here, and then here's your high one. Here's a high,
11.
here a high, there a high, everywhere a high, high.
Oh, I got that one wrong.
Okay? So the whole key to this is figuring out which is the positive and negative terminal of the battery. So remember, when you look at these diagrams, the big side, that's the plus, and we always use the traditional idea of current coming from Ben Franklin, and that's the direction it's going to go. So if you look at what's happening, so this current is coming out here like this, and then this current is going like this. So what's happening is that it's the log jam, okay? So when it gets to this bulb, because you have one current going in one direction and an equal current going in the other direction, it's like two opposing forces. You won't have any current flowing through it. So that's why this one on number 11, that middle bulb doesn't light up because you have two opposing currents flowing through that. Okay, so just be aware of that. Okay, anything else? Going once, going twice, sold. Get that handed in. So stop that. Okay, for those of you that are watching on the studio audience, I will scan this and send this to you. It was a mock quiz, okay? Not points, although I should tell, but no, this is like for 40 points. Here you go. Okay, anyway. All right, so on number 1, Louis, what did you do on number 1?
I'm sorry.
What did you do?
What did I do on number 1? I was being extremely dumb. So first of all, I started with P equals IR squared, and then I found P equals V squared R, and then I solved for R.
And that's about the only way you can do that.
Yep,
Wait, what?
yep. I went the long way. Just use P.
So I'm guessing you started with PIV
Yeah.
and you started with VERB.
No.
Is that what you got?
I started with I squared R.
We just got those.
Well, but that's where that comes from. So,
Oh, I guess I didn't go that far back, but yeah, I guess.
well, if you take this and you solve for current,
Yeah.
it's V over R, okay? Or if you solve for resistance, it's V over I. But no matter what, you get power equaling V squared over R. That's why I said you have to be fluent in the 3 languages of calculating power. So if you do this, you've got your voltage, which is what we run off of. It's just 120 volts squared divided by your resistance of, and then you're going to solve for, you're solving for resistance.
Unless you divide by power.
So you get V squared over power, and you should get about 170 ohms.
This is in coulombs.
Okay?
I don't know.
Ballpark.
And then I is in coulombs for a second.
Q's in coulombs? I thought. No. This capital Q's not in coulombs. It's in joules.
I don't
Right?
know, just go.
Let's go with this. Okay. Now, when you get to number 2,
That's just
okay?
not electric,
So
right?
you got the 480 milliamps. What are you going to have to do with the milliamps?
Take it times negative 10 times to the negative 3.
So you get 0.480
Yes.
coulombs per second, because that's what amps is, right? Now, how many, Louis, how many coulombs are there on one electron?
1.6 times 10 to the negative 19.
Okay, so let's think this through. Should your answer to number 2 be a really big number or a really small number?
Really big. Uh-oh.
Really big.
Hopefully really big. You're going to have a lot of electrons per
Yes.
second.
What? Oh, my bad.
Wait,
I went
said-
to number 3. My bad.
Are we supposed to use the
No, wire.
coulombs or the joules? Because I used the electron volts. Because I was like, oh,
No,
joules,
no,
I
don't
need
do
joules.
electron volts.
Oh dear. Dang it!
So just divide by 1.6 times
I still
10 to
got
the
the right
negative
answer.
19th coulombs per electron. And that's what that is, right? So that's how many coulombs there are on each electron. Your coulombs cancel out, your electrons flip up, you get coulombs per second, and you get 3.0 times 10 to the 18th.
18th? Oh wait, I got that too. Wait, I'm confused though
Yeah, that
because
counts.
it worked.
Well, because you
I said 1 electron
because
volt.
1 electron volt
One
is
electron.
1.6 times 10 to the negative 19th.
Yeah, that's what I did.
And so that's where that comes from.
But is amps not in joules per second?
No, it's
No, that's
coulombs
watts.
per second.
Okay, I forgot my what's it called.
Pay attention to your units.
I don't know what my units were, so
Well, I don't-
that was a good guess.
If you don't know, I don't know either.
coulombs per second.
Okay, when you get to number 3, you have resistance equals rho L over A. Now, let me give you a hint. This is something else you should be fluid in. The idea that volume is area, the cross-sectional area times your length, okay? So if you solve for area, that's volume divided by length. And if you substitute this in, you get rho L divided by volume divided by length, which becomes rho L squared over volume, okay? That's just a handy dandy thing to keep filed away in the back of your memory, okay? That this volume, if you have the volume, you can substitute that in, okay? So just keep that in like your bag of tricks, okay? Now, so what do you think you're going to do wrong on number 3 with that information? What's the most common thing that I'm going to see done wrong on this problem?
Square the
The radius.
diameter.
Yeah, that says diameter,
Right.
and you're going to
yeah,
use
yeah.
that as the radius,
I did it.
okay?
Louis, did you use that as the radius?
Oh my gosh.
It's like I'm psychic or something.
It's like you.
It's like I've taught
It's
this
like he's
before and
preying
I
on
know
our
what you're
downfall.
going to do
God,
wrong.
It's so dumb. You can't just throw us a bone, Mr. Burkamp. Throw us
I
a bone.
could.
Or draw us a picture. You know?
You
Diameter?
all are capable of drawing pictures.
I know, but like sometimes like
So you have your resistivity, 2.44 times 10 to the negative 8th ohm meters. And then you have the length, which is 16 centimeters, Louis, which is going to get changed into?
0.16.
Yep,
Okay.
0.16 meters. And then pi times
That's not 0.10 times 10 to the
0.0011 meters squared. And you get 1.3 times 10 to the negative 3rd ohms. Then what are you going to do?
But that by 0.866.
P equals I squared R.
P equals I squared R. And you should get 7.70 times 10 to the negative 4th.
Is this what our test is gonna be like?
7.72 as well. Sweet.
Cool with that.
We got some
Yes.
AP questions. Yes.
I know.
Okay? Now, then you get to number 4. So what's one thing you have to find on number 4?
Why don't I just
Oh, I think it's still 2.
You have to find that Q value. Q here is not charge. This is thermal energy in joules.
was good?
It doesn't make sense. Wait, what?
M delta T C sub P. So you got the mass, do all that, you get
19,000.
19,106 joules. So that's how much energy that it takes,
Right.
okay?
Divide by the resistance.
Now, you have the resistance and the voltage. So what can you do with that?
Power equals V squared over R.
Power equals V squared over R.
Yes. Yes, sir.
And you do that, you get,
90 watts, which is in joules per second.
which is joules per second.
And then you take your
Then
19,000.
what?
19,000 times 1 seconds over 90 joules.
So
Take
you're
it
just gonna
into
multiply the
seconds.
two numbers together?
No, you have
One
to
over
divide by
90.
90.
Oh, okay, yeah,
Yeah,
divide
so
by
that the
90.
joules cancel out, and then you get seconds.
So you're gonna take the joules, divide that by joules per second, you get
212.
212 seconds. Okay,
Yes.
cool with that.
Jackson, did you get that answer?
I didn't know what to do. I got lost. I
Okay,
confused myself.
find your energy, find your power.
Yeah.
Watts is joules per second.
Yes.
We're good at that, Lou?
Wait, so which one's coulombs?
Coulombs is charge.
Coulombs
Amps
is
is,
charge.
wait, amps is coulombs
Coulombs
per
per
second?
Yeah.
And amps is coulombs per second.
I'm a little lost.
Wait, what's voltage?
What's,
Voltage is joules per
You gotta
coulomb.
do
That's energy.
oh
the
gosh,
amperage.
voltage
and
is
then
joules
that's the
per
one
coulomb?
minus
I didn't know.
Now, when you get to number 5, what do you have as the equivalent resistance?
10.
10 ohms.
Yeah.
Because you've got the two that are in parallel, so you got
One back to the
1 over 15, the inverse of that, plus 4, and you get
10.
10 ohms. So then, which one of those, the 10 ohm, when you're talking about the ones that are in parallel, the 10 ohm or the 15 ohm, which one is going to carry more current? The 10 ohm or the 15 ohm?
The 10.
The 10 ohm. So you need to find the entire current, so you're going to vert it up, and the entire current is going to be 2.0 amps. So that's the current in the whole thing. So that's going through resistor 3, and then 1 should be 1.2 amps, and 0.8 amps.
Yes. Wait, so when it's
There you
in
go.
series and there's multiple resistors, the amps will between in each
Current will be
one.
the same.
I mean, the
If-
current
if
will
you- if-
be what's
If
it
you have
called?
like 2 resistors that are in series,
You
it's
have to
going to
do
have the same current.
yeah, but when you do V equals IR, you have to use the overall resistance. Okay,
Yeah.
sounds good.
Okay, kids.
That wasn't too bad.
So no, you don't have any homework. Okay. So
Maybe study a little.
yeah, you might. If there's a chapter that you read, it might be this one.
23.
Oh,
What?
That's what his question.
No.
Oh, did you have a question?
I have a question for
Oh, okay. You have a question.
before I ask them. Would you be allowed to donate cents to the,
Like, it's not just change, but I have change from donuts this morning. So I have like,
It's not
it's
just.
more than 59 cents, but am I allowed to count the 59 cents towards that?
Yes.
Okay.
oh, we're doing that. I forgot about that.
money's
so
money.
tiny.
The goatee
Huh?
is the goatee
I feel like there's not
happening?
even enough time.
Well, we'll talk about that on Monday because this week is so screwed up. I wasn't going to. I wasn't going to start it going out to a conference in DC anyway.
So,
So
fine.
Okie doke.
IR to get you.
Is that it?
that's it.
Okay, bye guys.
Is this like a short?